Yeah, of course. Thank you very much to the organizers, so Elisa, Marcos, and Ricardo, for having me here, and it's a pleasure to be here and to speak, especially in this wonderful venue, and to interact with everyone. So thanks again. So the topic of my talk is about two types of materials, polycrystals and composites. And in the spirit of the talk, we'll take it beyond elasticity and work in finite crystal plasticity. So before I give you an overview of what's going to come, I'd just like to acknowledge my collaborators. So this is Dominik Engel. He was involved in the first part of the project. He's now a postdoc in Eichstätt. And the second work is based on a series of papers together with Fabian Christowiak and Elisa Davoulier and Rita Freire. So now let's get started. Now I just need to see how this, So I'll start with a bit of an overview and explaining the main modeling assumptions, and then also introduce a key result from the literature that will be useful along the way. And then about polycrystals, we're interested in to understand the effective material of such a crystal when each grain can undergo single slip in different directions. And it's somewhat natural to expect that there will be some complex interplay between the slip mechanism, microstructure formation, and also the texture of the polycrystal. And this is what we'd like to capture. But a full characterization of the set of attainable macroscopic deformations at this point seems a bit beyond reach. So what we're going to do is we're going to look to find inner and outer bounds for that set. So then we have a part 2, and this is about layered composites, so with a high contrast component in there. So here we'd like to prove gamma convergence results for homogenization into special versions of the model, namely one with and without linear hardening. So in both these applications that we have in mind, the common feature somehow is that they can be represented as variational models with non-convex differential constraints. And another thing they have in common, they both share this strong interplay between anisotropic behavior that comes from the restrictions on the slip direction, and on the other hand, the geometry that comes in at the mesoscopic scale, so in terms of the grains or the layered structure. And this will have as an effect that we find a strong restricted effective material response, which we'll see in the following. So basically that's the program. And now let's start on the setup. So we have a reference configuration omega, we have our U, our deformation, and now we need a good model for plasticity in the large strain setting. And so there's not just one way of getting there. There have been several approaches to that over the years, and very nice recent approaches, so maybe we'll hear some about this during the week. But that's why I decided just to keep it short and say that we're going to use a classical approach according to Kröner-Lee, where we use a multiplicative decomposition of the deformation gradient into an elastic part that captures the local rotation and stretching, and the plastic part that encodes the reversible deformations and the history of plastic flow. There's also a nice paper by Conti and Reine who give a justification of that decomposition from a micromechanic. So then, next thing in our list here is the time-discrete variational approach along the lines of these papers here. So it means we discretize in time, in each time step solve a minimization problem, and go from there. But then a disclaimer at this point is that we're not going to look into evolutionary effects in this talk, and also no challenges due to pre-existing microstructure. So we'll just focus on a single time step, actually the first. And the energy that we're going to consider in that incremental first step is of that following form here. It's an integral over a condensed energy density that depends on the deformation gradient, and this condensed density here is like in the box. You get it by taking elastic, plastic, and dissipative energy contribution and optimizing over all possible decay. Now, when we work with materials that have a crystalline structure, plastic light, I think this is also well known, happens when neighboring atomic planes move, and that doesn't happen by breaking all atomic bonds at the same time, but instead it's induced by the movement of dislocations throughout the material. And this plastic light happens along well-defined slip systems, so they consist of a slip direction S and a slip plane normal M, so these are two orthogonal unit vectors. And now depending on the polycrystalline lattice one has at hand, there's different numbers and orientations of single slip systems, And yeah, for example, if you look into FTC lattices, there are 12 of them. But now there comes experiments which show that in principle, even though there may be many, in practice, only quite a few number of slip systems tends to be active at the same time in a material. And that's why it's justified also to look into smaller numbers of slip systems. And this is related to the fact of latent hardening. And there is even, single slip is even common, especially at the onset of plastic deformations when dislocations start emerge and begin to move through the material. Now, with this in mind for general context, then I'd like to focus from now on just on the simple case of single slip system in 2 dimensions. In that setup here, we find that our plastic strain here is given as identity plus gamma as tensor M, so where gamma denotes the amount of slip that we have. And the second assumption that we're going to use here is rigid elasticity, so assuming that the elastic part is really locally almost everywhere of a rotation. And this assumption can be justified to consider that in many metals, plastic strains are much larger than the elastic one. Now we put everything together and find that the total deformations that we want to consider are exactly those that have deformation gradient in the set MS that you see here, so matrices of this form, and this can equivalently be written as matrices that have one determinant, so we have incompressibility here, and we have also normalization in the direction S, so now slip direction, saying norm of Fs is equal to 1. Just for later, here's a bit of a shorthand. Now in terms of energy, this means for us that we have this elastic energy contribution coming from the rigid elasticity assumption. For the sum of plastic and dissipative energy contribution, we assume that is given by a pth power of the amount of slip here. And we distinguish 2 cases in the following. So P equal to 1 corresponds to a model without hardening and dissipation. And on the other hand, we have P equal to a case with linear hardening. Okay, now we take that all, plug it into a formula for the condensed energy, and this is what we end up, the W that you see. Now, also, say maybe that once again that it's finite on the set MS. Now, since we're interested in energy minimization in the long run of the according energy associated to that, of course, once we add external forces or boundary values, it's important to observe that this is a non-convex energy. It's not even quasi-convex, so we know that may lead to oscillations in minimizing sequences and then eventually to the formation of microstructure. Now, I'd like to show you how microstructure can form in our model, because I think that's quite intuitive. So let's take a sample material here, which we split vertically into parts. Now we shear the 2 parts, but we go opposite directions, so we shear like this. So this gives us following. Now we rotate the individual components here, one in that direction, one in the other, to end up with a structure like this. Now we repeat the whole procedure on a finer and finer subdivision of our sample here, and eventually the picture will look, if I can draw it correctly, it will look like this, where you see that what happened effectively now is that we had a stretching of our material in vertical direction and a compression or shrinking of the material in horizontal direction. So through this lamination procedure, we see that also other macroscopic deformations than just simple shears can occur. Okay, now how to deal with formation of microstructure? I think everyone knows this is here very well. The method of choice is relaxation. So we're going to work with the quasi-convexification of this energy density W here, which corresponds to a macroscopic strain density. And so you see the formula here. You take the energy per unit volume and you optimize over all possible microstructures or Lipschitz functions in mathematical language that satisfy the boundary conditions Fx. So as nice as this formula is from a theoretical point of view, of course, it's really hard to deal with practically. And this makes the following theorem by Ponti and Keil even more impressive, because they managed to give characterization, so explicit representation formulas, and also very elegant ones, for these quasi-convex envelopes. So you see here for the case P equal 2, and here for the, P equal 1 here, and P equal 2 over there. So the expressions of these densities differ, but what they have in common is they share the same set of matrices where they are finite. So this is the set NS, which you get by taking matrices with one determinant, so the incompressibility is preserved, and the norm of Fs is now not equal, but smaller or equal to 1. So this set has been shown to be exactly the quasi-convex hull of the set MS that we had on the previous slide, and it also coincides with both the polyconvex and the Rencontres hull. So this NS here is what we should keep in mind because it will be important for later. So we think of it as the set of attainable macroscopic strains for our single crystalline, single slit model. Okay. With this, we may move on from single crystals now to polycrystalline structure. These, so as a definition for a polycrystal, we follow along the lines of the work by Ball-Carstensen. And we assume for us, so a polycrystal is a pair of, on the one hand, a bounded Lipschitz domain and a map from our star from omega into SO2, so a rotation-valued map with a property that you can subdivide your omega into finitely many subdomains on which the R star is constant. So in that sense, the R star captures both the geometry and the orientation of the polycrystalline grain. Okay, so here. In the following, we'll also distinguish between interior and boundary grains. So I think the coloring is quite intuitive. Then we'll have so-called boundary dual points, which are points at the boundary of the polycrystal where two or more grains intersect. And we can also illustrate here for completeness the set, the map R star here with the little arrows here, where the arrows point in the direction of the first component of these rotations associated with R star in the respective grain. Now we assume that these grains are elastically rigid and can be deformed plastically only in the direction of the respective arrows. And by doing that, we end up with a microscopic energy density, so that you see in the blue box here, which is exactly the heterogeneous analogon of what we've seen in the single crystal case. So then we can also learn from the single crystal case and in analogy define a corresponding macroscopic strain density. So a similar approach has also been done in the context of polycrystalline shaped memory alloys in the work by Kohn and Bhattacharya. And eventually now we can say, how do we get our attainable macroscopic deformations? Well, these are exactly those for which this density here is finite. Or you can phrase that also differently by saying it's exactly those matrices F, so that this inhomogeneous differential inclusion problem, PM, with affine boundary values Fx, has a Lipschitz solution. So our plan in the following will be to understand as much as we can about this set of attainable macroscopic strains, which we call Fm. And what we'd like to do is like squeeze it in from inside and out, so find geometry independent inner bounds and outer bounds that result from compatibility conditions with the boundaries. So in both of these situations, for both of these bounds, we're going to need a tool, and namely a relaxed version of this inhomogeneous inclusion problem. And so here I'll show you how we get there. If we think back to the single crystal case, we remember that, so this is the case when R star is constant, we know that Fm, this is the theory by Quantile, corresponds exactly to the set N in the right slip direction, though this is R star E1. And now with this as inspiration, we'll define the relaxed inclusion problem by simply taking the previous one and replacing M by its quasi-convexification N. Okay? So this gives us a set here. So then we know that trivially any solution to Pm is also a solution to Pn. And we have also the reverse connection. If we have a piecewise affine solution to Pn, we know that we can construct a Lipschitz solution to our original problem. And so the way to prove that is just take the construction by Quantile and apply it to the affine pieces intersect with the polycrystalline grain. Okay, with that, we're ready to go for the geometry independent inner bound. And the idea here really is to use globally affine solutions to the relaxed problem. Because as we just heard, this allows us to construct solutions to the original problem. So what we have by that is that we take this intersection here, it's a finite intersection, which we call Tn, that this intersection is contained in our set Fn. And in contrast to the right-hand side here, this Tn only depends on the image of the texture map and is therefore independent of the geometry of the polycrystal. So in the literature, it's pretty common to call bounds that are associated to constant strain solutions Taylor bounds, and this is where we borrow our terminology from. So we refer to this bound as the Taylor bound for Pn or just Taylor bound. Now, usually polycrystals have a large number of grains, so in principle, there's a lot of intersections to calculate here. But the next theorem shows that things are actually pretty simple, that it's enough to only take 3 of them. And here I give you the statement of the theorem. If we have our texture map R star, which takes these values here associated to angles in increasing order, so we can assume also that the first one is set to 0, no restriction. Under this assumption, we find that the Taylor bound can be determined by just considering the 0 angle and the 2 angles that frame the angle pi over 2. So that's what's here, and I've also an illustration here in the picture. So to calculate the Taylor bound associated with these orientation angles, it's just enough to take these red guys here. So theta 4 and theta 5 are closest to pi over 2. Okay, so the calculation behind that, I have to say, is not really pretty to put on a slide. So instead, I'll show you just a corollary, which helps us to characterize the cases when the Taylor bound is actually trivial. So it trivial means it's equal to SO2. And the criterion here is that the 2 angles that frame pi over 2 are at most pi over 2 apart. And the proof idea is really not hard and easy to see just in one single picture, so I'll show you. So if we have a polycrystal with these 5 directions, we know from the previous observation that this Taylor bound corresponds to the intersection of the 3 red ones. Now we add another one, the blue one, theta tilde, from which we know that it doesn't change anything if we take this intersection in addition to add this intersection to our Taylor bound, because theta tilde is further away from pi over 2 than theta 4. But now we see that these 2 here, the that's associated to A3 and theta tilde, their intersection only contains rotations because, I mean, they have a 90-degree angle, and so the Taylor bound needs to be trivial. So if we think of samples, so randomized polycrystals, so crystals with a random orientation of the slip directions, we consider, rotation angles that are uniformly distributed, and then we can calculate the probability of finding a trivial Taylor bound independent of the number of grains that we have. So the formula is down here, and you see as you let k to infinity that for a large number of grains, it's very likely to find actually a trivial Taylor bound. So far on inner bounds. Now we can move to outer bounds, where we use compatibility conditions along the boundary grains. And yes, I think a most famous rank 1 compatibility condition is the Hadamard jump condition, which I've stated here just very briefly in a very basic form. But since then there have been many generalizations and extensions of this result. So just a list of a few authors who contributed there. So they cover the Lipschitz case of maps with higher regularity, like continuous differentiability up to the boundary. There you find the curved interface case, or even situation of moving interface. So the version that we're going to work with here is this theorem, which is essentially a special case of a much more general result by Boll and Carstensen. A different way of looking at it is that it's a curved interface version of this paper by Iwaniec, Verchota, Vogel, which one can also prove based on their work via a standard blow-up argument via Young measures. Now, maybe I'll just draw the statement of the theorem instead of read it out. So if we have a bounded Lipschitz domain U, and we have a curved, potentially curved interface, gamma cutting it in 2, then we have our 2 sides U1, U2, and also we fix a point here on the interface for which we know that the outer unit normal Ux0 exists. Also, we assume that we have a Lipschitz map that whose gradient is equal to A almost everywhere here on the right, and on the left, and lies almost everywhere in B here on the right. Then the conclusion is that A is nu x0 compatible with the Poly convexification of VC, so which tells us that essentially A tensor nu x0, so this tensor product, lies in the difference of the polyconvex hull of B with A. So now what we do is we apply this, exactly this result, to our boundary grains, and also exploit that the polyconvexification of M was our set N. Okay? So by doing so, we then find that the set Fm is contained in what we call here T and delta. So the delta stands for boundary and somehow indicates that there are restrictions coming in through each compatibility conditions at almost every boundary point. So almost everywhere, I mean everyone except where outer unit normal doesn't exist or a point there's a boundary grain. A boundary dual point. Okay, so again, it's a condition, but again, it's really very hard to work with. So again, there is a simplification that comes from the following observation. So if you sit in one of the grains, where along the interface there is an outer unit normal that is at some point orthogonal to the slip direction. So it's the case for the green boundary grains that are colored here. In that case, you can show that all the constraints along the boundary just reduce to a simple condition, namely that F lies in the intersection of N R star transpose with respect to that specific grain. Now this is what we use to find another outer bound, namely we take all the intersections of these terms here associated to the green grains and have another bound for our set Fm. Okay, so of course this is potentially a larger bound, so a reverse bound, but you gain a lot because you get a bound that is really handable in the sense that it has the same structure as these Taylor bounds that we discussed earlier, and there we know how to calculate them efficiently. So in that sense, this could be seen a bit. Good, so now I have two examples. First one is polycrystals with sufficient symmetry. So by sufficient symmetry, we work with the notion in these two papers, saying that essentially the set of attainable macroscopic deformations is invariant under a certain orthogonal transformation. If we then have a green boundary grain, so remember the previous slide, then we can apply this symmetry condition iteratively and in that way show that SO2 is an outer bound on our set Fm. Okay, if SO2 is an outer bound, then the polycrystal has no option other than being fully rigid. Okay, so I have another example. This is bicrystals, like in this sketches here. So also here you see that we can exploit our interaction between the boundary, the slip directions and the geometry of the grains to show that we have an outer bound that matches the Taylor bound. Okay? So Taylor bound is optimal. Now you may wonder, I mean, in all the examples that we saw that the Taylor bound always represented the set of attainable macroscopic grain. And so the question is, yeah, Taylor bound was optimal. Is it always optimal? And yeah, the answer turns out to be no. And this is formulated in this proposition here. But for us, I have to admit, it was not that obvious to see at first. So in the end, there's a proof. And this is based on a construction of polycrystals inspired by the literature on stress-free martensitic inclusions. And specifically, there are two papers that we took inspiration from. So it's these two, where the authors discuss a rotated shear approach. So where they construct locally volume-preserving piecewise affine deformations, like in this picture here. Okay, so the difference is, so while in these papers here, the interior square here, so that's why rotated square construction is rotated, this is not enough for our construction, for our needs. So what we're going to do is we're going to shear it. So that's why we call what we're doing a sheared square construction. And here I have some details about this procedure here. So in the first step, we select two slip directions, and we make our lives easy. So we take E1 and E2 because this gives us then a trivial Taylor bound. So on the other hand, next step is we decide on our set omega, which we take as a square, but we tilt it slightly to avoid compatibility conditions from the boundary frame. Then comes the next step, and this is to construct finitely piecewise affine solutions to this homogeneous inclusion problem. So we want the gradient of V to lie in the union of NE1 and NE2 and have affine boundary values Fx. And important, in order to prove our claim, we need F to stay away from SO2. And the way we solve that problem is by, I said it already, so shearing the center square here. So we say that gradient of U equal to S, restricted to S as identity equals gamma E1 tensor E2. So this is a matrix in ME1, therefore contained in NE2 and therefore admissible here. Then we take a next step and use rank 1 compatibility conditions to deform these surrounding triangles here. And in the final step, so we still have 1 degree of freedom left. So our shearing is we take the shearing parameter and tune it so that our boundary values stay away from SO2. Okay, so now you may wonder where are the polycrystals. Yeah, so they're coming in the next step. So now we take this construction and from that define our polycrystalline structure. So we color the individual pieces here, the connected components here, according to that color scheme. So we take it yellow if the gradient is in NE1 and blue if it's in NE2. If it's in SO2, we take whichever we like better. And this way we end up with a polycrystal with a non-planar interface. And then we're almost done because there's the final step missing. There's just to take this piecewise affine solution that we just obtained for the relaxed model and construct from it a solution for the original model. And this finishes the construction. Okay, so this was so much on the polycrystals. Now I'd like to move on to the second part on the bilayered composite. So geometric setup is the following. So you have a layered material with layers, horizontally and periodically arranged. The two parameters here are the relative thickness of the soft component and we could call lambda, and here we have a length scale parameter epsilon, which describes the thickness of two neighboring layers. As for deformation behavior, we assume that the layers are fully rigid, and in the soft layers we can have deformation along that single slip system. So here we use essentially the material model that we introduced in the very beginning. P can again be either 1 or 2. And with this setup here, we obtain an energy that has a contribution coming from the stiff and soft components. And if we plug our formulas from above in, we can also rewrite that in a form like this. So as a single, just one integral functional subject to a constraint, so that U lies in the set A epsilon, meaning that the gradients are in the set MS, so of rotated shear deformations locally, and gradient of U lies in SO2, so in the set of rotations, even in the stiff component. Now, since we're interested in the effective behavior of these models here, the goal is to determine the gamma limits as epsilon tends to 0, which is due to these constraints a non-standard gamma limit. Okay, so first let's look into the case P equal 2. And the first step somewhat in the analysis is to find a good way of handling these rigid components. And so here I've just quoted a very well-known, I think everyone knows that, rigidity result by Reshetniak, which says that if you have a W12 function on a Lipschitz domain, so in particular connected, and the gradient of U lies in SO2, then you know you have a rigid body motion. And clearly, I mean, this result fails as soon as your U is no longer connected, as is the case with our rigid component. However, because of this specific arrangement of these components into these fine layers, it is still possible to derive some restrictions on the macroscopic material behavior. So this is like an asymptotic result. And that's why we speak here of asymptotic rigidity for layered structures. And so the theorem reads as follows. So if we have a sequence of W12 functions that converge weakly to some limit U and that take whose gradients lie almost everywhere in SO2 on the stiff components, so just there. Then we know that our limit deformation here has the form Rx plus B. So now it looks almost like it did before, but now watch out. Here R, it's a Sobolev map, and so is B, but it's independent of the x1 direction, so the layer direction. Now if we incorporate more assumptions into the model, namely incompressibility or local volume preservation if you wish, so in any case we have that for our plasticity model, then we can prove even stronger restrictions on the limit deformations, namely that they have to lie in the set we call A, so they are globally rotated shear deformation. So you can shear in horizontal direction and then rotate everything globally. And formally, that means that the gradient of U is really constant rotations times identity plus gamma E1 to E2. So with this result as like the main tool, we can then formulate our homogenization results in terms of gamma convergence, along with also compactness that comes with it. So let's have a look at the gamma limit. So it's finite on the set AS here. So these are the globally rotated shear deformations, and we can get additional restrictions coming from the orientation of the slip systems. So this is what this KS encodes. So in the case that S is E2, the slip system is orthogonal on the layer, so intuition is that it would get blocked, and this is exactly what we see here. So no slip is possible at all. In the other case, when the slip system is parallel to the layers, you would say, yeah, it's free to go, and this is what's reflected here, so no restrictions. And in all the other cases, we get some unidirectional shearing. So let's look at the energy contribution. So the first one here is a homogenized hardening contribution, and then we also get an additional linear term, which reminds a bit of a dissipative. Okay, so so what I like about this result is that it's a homogenization result that is fully explicit. So in a sense, so the formula explicitly shows dependence on lambda on S, and in that sense, this is quite rare to find in homogenization theory, where one has often to deal with rather abstract homogenization formulas in terms of multi-cell or single-cell formulas. Okay, then also another remark, and together with Elisa, we recently looked into the structure of minimizers for this problem, where we could prove some partial uniqueness results and also derive optimality conditions. Whereas P equal 2, let's see what we have for P equal 1. So here we'll assume for simplicity that we have the slip system parallel to the layer direction. So in that case, we have the same steps to take. So the first thing is to prove a suitable asymptotic rigidity result. But now this time we need it in BV. So precisely we start off with a sequence in W11 so that the gradient of U epsilon is an SO2 on the stiff parts, and we converge weakly in BV. And then we recover again the same structure of the limit deformation as before, just now R and V are BV functions. So now we need to incorporate incompressibility to get refined asymptotic result. And we do that again here by requiring the determinant of gradient U epsilon is equal to 1 almost everywhere. And we suppose on top of that that we have uniform control on the first column of the deformation gradient in the L infinity norm. So if we have that, we can use weak continuity results of the Jacobian determinant and derive that our limit deformation here really lies in the set A, which is characterized by these two expressions here. So what do they say? So the first one here is the absolutely continuous part with respect to the Lebesgue measure. This looks almost like the gradients that we had seen in the case P equal 2, but now R is a BV function that has vanishing absolutely continuous part. So on the other hand, so this was the absolutely continuous part. For the singular part, we see that it vanishes in E1 direction. So intuitively, what does such a limit map in A look like? So what can happen here is really the material can break up into different pieces here, but I mean the fractures are horizontal only, but after that you can have individual shearing and rotation of your component. Now the previous theorem also showed that basically the limit deformations A they provide necessary conditions for the kind of homogenization result we're after, so of the effective deformations that you can observe. In that sense, if you're aiming for a homogenization result, it's somewhat natural to ask which of these elements in A can you also approximate admissibly, so with admissible deformations in the set A epsilon. And here we have a few examples where we can do that. So we can approximate simple jumps, even though I have to say, we do that by piecewise affine deformations. And you see, this is the illustration of the construction, and this is really not painless. So even a simple jump already requires some work. And we can then stretch that also to finitely many horizontal jumps, but approximating an arbitrary SBV function in A is something we cannot do at this point. So then we have another class, namely this class A parallel, which you can think of like parallel jumps in layer direction. So basically what we have illustrated in this picture here. And in this case, the maps are essentially one-dimensional, so their constructions are much easier, and we can exploit the one-dimensionality of this U to split it up into 3 components, namely a W11 part, a jump part, and a contour part. And for the W11 part, we do a construction that is built on the idea that you compensate for the rigid components by simply shearing more in the softer ones, so quite intuitive. And in the other 2 parts, we do a density argument together with a rescaling argument where we suitably stop and accelerate our variable. Okay, so this is the sets we can approximate at this point, but for general sets, for the general set A, approximations are currently not available. So there's really not much room to play with, and this is a bit tricky. So what did we do? To get around this. The way around was that we used a common trick, namely we decided to introduce a regularization. And principal regularizations are pretty common also from the modeling perspective. If you think of models involving Hessians of deformations, for example, you find that. So this is what we decided to do. And with this regularization, in principle, we're only doing a partial regularization, namely to penalize oscillations in layer direction. We can then prove the result we wanted. So what we do is we add this blue box here to our original model. This is a penalization for layer oscillations in the direction of the layer, and involves higher order, so second order derivative. And by introducing that, we can then derive the desired gamma convergence result here, showing that these E epsilon delta gamma converge to this E delta here, which, and now you recall the set from before, are exactly finite on the set A parallel. And an alternative way of representing this A parallel is it's all those matrices in A, so that R is constant in SO2, and the E2 direction of the singular part is really parallel to the first column of this R, so parallel to RE1. Okay, so I think in terms of time, in the interest of time, I'll skip the details of the proof, but I'll just give you the essence again. So what really made the difference here is that adding this regularization here helps us to avoid a tricky issue related to compensated compactness, and once this is out of the way, we can get gamma convergence result. Okay, so with that, I'll summarize. So the talk had 2 parts. So in the first part, we looked into polycrystalline structures and derived inner and outer bounds on the set of attainable macroscopic deformations, and also showed that this inner bound, the geometry-independent inner bound, the Taylor bound, is not optimal in general. And then in the second part, we discussed bilayered composites and proved, first of all, asymptotic rigidity results, both in the Sobolev and the BV setting. And then we're able to prove gamma convergence results that were explicit, so for the case with linear hardening, and after regularization also in the case without any hardening. And so I think I'll stop with that. In case you're interested in more details, here are the references. Thank you very much.
Yeah, thank you very much, Carolin. The talk is now open for discussion. As you might have noticed, the talk is recorded, so I ask you also for the questions to use this microphone. Marco is going to run around and bring it to you. Please.
I was wondering about the asymptotic rigidity results. So you proved this in 2D. Do you have a sense of whether something similar might hold in 3D and under what kind of conditions?
Yes. Okay. So I can go there. I think so. So I only spoke about this one specific case here, 2D. But I mean, we have really worked on that in arbitrary dimensions. So. But okay, so then we need to say, what does arbitrary dimensions mean for layers, right? Because once you go from the 2D setting to the 3D setting, the question is, do these layers generalize into layers, or do they generalize, for example, into fibers? And we have asymptotic rigidity results in either case. One is a collaboration with Dominic Engel and Antonella Ritorto, and the other is, like in this paper, with Fabian Pastodia. So we have analogous results there. Of course, in the fiber case, I mean, we have less rigidity because, I mean, we have one codimension more of degrees of freedom. But yeah, so analogous results do hold. Thank you.